Great. Good morning. I'll be talking about tensor decompositions and their applications. So this will be the second in the talks about algorithmic aspects of inference. So, I think it's a good way to start off with some stories. So let me actually tell you where tensor decompositions fit into the bigger scheme of things. So last time we went back to 1894. We'll go a little bit more modern this time, so 1904, almost from this century. And so there was a very famous psychologist, Charles Spearman, which he invented factor analysis. And what I want to do is I want to tell you a little bit about his experiment and then some of the mathematical subtleties to this and how tensor decompositions are something that can be thought of as addressing that. So Spearman had, I guess, what's a kind of controversial hypothesis. So he believed that there are only two types of intelligence, inductive and reproductive, which the ability to make sense out of complexity and the ability to store and reproduce information. Sometimes it's colloquially described as mathematical and verbal intelligence, although that's not really faithful to what he was actually talking about. But what he suggested as a way to try and test out this hypothesis was a very simple idea, which is powerful, and we see all over the place now. So he took a collection of students, 1,000 students, and he took about 10 tests. And he had each of the students take the tests, and he got their numerical scores, and he arranged all of that data into a matrix. So each row represents a different test, and each column represents a different student. And what he suggested was that this matrix could be approximately written as some rank 2 factorization. And he hoped that there was some magical factorization, which it would just be staring you in the face the fact that this rank 2 matrix represented this inductive and reproductive types of knowledge. So what he actually hoped was not only that this matrix was approximately low rank, but that it even had a meaningful interpretable low rank factorization. So what do I mean by that? So you could hope that there's some nice rank 2 factorization where now for a particular row which represents a test, you can think about that row as indexing into the first of these matrices, and it's just a length 2 vector that represents for a given test how much does it test inductive reasoning and how much does it test reproductive reasoning. So that would just be a simple length 2 vector. And the same way for each student, that would be a column in this matrix, you could take the corresponding index, the length 2 vector in the second matrix, and that vector would hopefully represent the student's innate abilities for inductive and reproductive reasoning. So what he hoped was that there was some magical low rank factorization, which was not only low rank, but interpretable in this way, that you could really look at it and see inductive and reproductive reasoning going on there, and that together this would explain the data you were given, so that if you were given any entry in this original matrix, how a student did on a particular test, that it could actually be explained as the inner product of just these two different length 2 vectors. Yep. No, so he just took data that was actually available to him. And in fact, one of the central issues here, so this is called factor analysis. So this is actually the origins of factor analysis. The basic idea behind it is conceptually you want to take a ton of observations. So in this case, all of your observed data in this large matrix and try and explain it away using much fewer unobserved or latent variables. So these latent variables in this case would be these hidden features of the test and the student that together roughly determine how well the student actually did on the test. So in fact, there's a really subtle issue going on with factor analysis because a lot of the times the way it's set up is just this way. You take some matrix on the left-hand side that represents your data, and then you take some low-rank decomposition. But which low-rank decomposition, and how do you actually know if there is a good low-rank decomposition that's not only low-rank but also interpretable? How do you have any hope of finding that true decomposition? So what's really, the subtlety underneath it, let me phrase it as it's often called the rotation problem. So the idea is that imagine there is some true factorization that really tests Spearman's hypothesis and validates it. So there is some way to actually take some matrix of data and represent it as a low rank product of A times B transpose. And this is the part that's hidden that we're actually looking for. The issue is that we can actually apply any rotation to the data and still get a perfectly valid factorization. I can take any rotation matrix R, and R transpose its inverse, and if I insert R times R transpose inside, I'm doing nothing. But now I can collect the terms and think about instead A times R is my new matrix, and R transpose times B transpose is my other new matrix. In fact, you could do this with any invertible transformation, T and T inverse. So you could imagine that what if there is this nice factorization that really shows you that this is what's going on, that there are two types of intelligence. Well, you could apply a completely arbitrary rotation and mix up all of your data and get something that's totally opaque and difficult to interpret. And you wouldn't know if the reason you got that data was that there was a hidden factorization out there that you just didn't find. So that's the rotation problem, but let me actually rephrase this problem in a way that will bring us towards a solution, which comes from tensor decompositions, is that what's really going on here is this is just another way to reformulate it, is we're given this left-hand side M, and it really is low rank or approximately low rank. So it's summation over I from 1 to R, so there are R hidden factors of AI times BI transpose. Then the issue is that actually information theoretically, this is not a well-posed problem. That you can't actually recover the AIs and BIs uniquely given M without imposing some really stringent conditions on AI and BI. One thing that you could do for the right-hand side, this is very counter to people's intuition, is you could impose something very stringent like the AIs are all orthonormal and the BIs are too. And then there are reasonable conditions under which you really could recover the AIs and BIs. But what that would be akin to saying is that these two types of intelligence in Spearman's setting are not just the only types, but they're actually uncorrelated with each other. So the issue is that if you actually have much weaker conditions on the right-hand side, these AIs and BIs, you can't find it from M, but you will be able to find it from a tensor if you were given a tensor instead of a matrix. So really, the theme behind this talk, it'll be in two parts. We'll be first showing even conceptually how tensor decompositions can solve these types of rotation problems, how they lend themselves to much stronger uniqueness properties, and even in one very surprising case, an actual interesting algorithm. And then how you can apply it well beyond factor analysis to lots of different problems in inference and machine learning. So it'll be in two parts. So the first part, I'm really just going to be teaching you the basics of tensor decomposition. There's a kind of fun talk to give because the history is so muddled that it's a little fun running a comb through it. Some of these things have been rediscovered many, many times. And then the second part, I'll tell you about some applications to phylogenetic reconstruction and something called pure topic models. All right, so let's talk about tensors. So tensors sometimes sound big and scary, but they're not so scary. So in fact, we're all used to tensors already because matrices are just one type of tensor. They're an order 2 tensor because you access the entries of a matrix through pairs of indices. Now a third order tensor is going to be the main character in this talk. We could talk about higher order ones, but we're already going to see some of the gains about talking about tensors from the third order case, so I'll focus on that. And all they are they're collections of numbers which are not indexed by pairs of indices, but triples, I, j, and k. So you can think about tensors in many different ways. You could think about them as stacked matrices. But the really important thing is why they're not just collections of numbers and what algebraic structures are you going to be able to exploit. So the crucial thing is what is a rank 1 tensor, and from there we'll understand what low rank tensors are. So a rank 1 tensor is very naturally an extension of what happens in the matrix case. So in the matrix case, a rank 1 matrix is just the outer product of two vectors. Well, in the tensor case, it's a higher order outer product. So if, for example, you have a rank 1 tensor, then underneath it you have three vectors, A, B, and C, and your entry at I, j, k in the tensor is just the ith entry in A times the jth entry in B times the kth entry in C. And notationally, I'm going to introduce this notation. So this is often called, in this setting, where T is a rank 1 tensor described by these vectors A, B, and C. You write it as T is the outer product of A is the tensor product of A times B times C. And just to make sure we're on the same page, then in the case of matrices, we get a very familiar notation. So if we had two vectors, if we take A times B transpose, that's the same thing as doing the tensor of A times the tensor of A and B. All right, so now that we know what rank 1 tensors are, they're a very natural definition, well, we can naturally extend it to what low rank tensors are. So a tensor T is rank at most R if we can write it as the sum of at most R rank 1 tensors. So a very simple definition. Yep.
So I know there are different definitions of ranks of tensor, of higher order tensors, right? Is the rank 1 tensor compatible with the other definition?
Yes, exactly. So it gets a little subtle. I'll tell you a little bit more about that later. So this actually looks pretty innocuous right now, but I've hidden a lot from you that actually really goes wrong even with this definition. So I'll tell you more about that in a second. But first I want to give you some hope about why tensors should even hope to address our rotation problem. So the crucial thing is now let's think about what a low rank tensor is, right? So imagine we have some low rank tensor T. And what I claim is that now if we take a slice through this tensor, so imagine, remember, a tensor is indexed by triples of numbers. What if I fix one of those numbers? So I fix k, and then I range the first two indices. I get a matrix that's pictorially just taking a tensor and taking a slice through it. Well, that literally, from this definition, all we're doing is we're fixing which index of C we take out. So what we're actually getting is we're getting a low rank matrix, because we already have what its low rank decomposition is already, right? So slices through a low rank tensor are themselves low rank matrices. That's a really crucial claim. But the most important thing about this is that a tensor that's low rank is not just the collection of matrices that are low rank, because it's about the interrelationships between those slices. So the important thing is that, for example, each of these slices, whatever k is, you can see that not only is this matrix that we get out of this slice rank at most R, but in fact, the row and column spaces are all contained within the span of the AIs and the span of the BIs. In fact, something even stronger is true, is that each of these low rank matrices, which are themselves slices through the tensor, are just different scalings of the same set of rank 1 matrices. So it's a very strong constraint about how the different low rank slices interact with each other. So now actually I can tell you what the key idea is, what makes low rank tensors so much more rigid than low rank matrices. Remember, the fact that low rank matrices are not rigid is what's underlying the rotation problem. So the point is that, how can I be sure that I've actually found some of the true factors in this decomposition and not some arbitrary other things? So one idea is that if you really did, imagine I give you some collection of some rank 1 matrix, A tensor B, and what I can do is I can ask, can I take that one rank 1 matrix and scale it by different constants, for each of the slices, so that subtracting those rank 1 matrices decreases the rank of each of the matrix slices through the tensor. So one way that I could do this is if, for example, I set A is A1 and B is B1, and then, exactly on the previous slide, I had the right constants to scale that rank 1 matrix by, so that when I subtract it, I'm reducing one of the factors and reducing one of the ranks of each of the matrix. But the key point is that actually the only way that you can do this is if you really did find the true factors. So this is what makes tensors more rigid than matrices, so I'll prove that fact for you. But the idea is that in a matrix, there are many rank 1 matrices I could subtract from it to strictly reduce its rank that have nothing to do with the actual hidden factors. But in a tensor, I want the same rank 1 matrix to work for all of the different slices. And this is what actually convinces me that it's not an accident, that it really is one of the true factors. So we're going to see that. But first, let me add some caveats. So let me tell you all the things that go wrong with tensors. Because, this happens all the time, that you have something with matrices, and then someone has a brilliant idea. What if we try and work with tensors instead? Now, if you take something that works with matrices and you just dumbly try and extend it to tensors, you're going to have a really bad time. it's not going to work out well for you. So let me tell you why not. First, there are things like Hastad proved that actually computing the rank of a tensor is NP hard. That's not good. Computing the rank of a matrix is certainly computationally easy, and it underlies most of what we do. Even the basic the basic equivalent definitions of rank completely fail for tensors. So for matrices, you have the rank of a matrix is defined many analogous ways, like row rank equals column rank is not a completely obvious statement, and it's deeply powerful. It's completely false for tensors. Now, here, let me worry you even more. So by the end of this, you're going to be quite worried, I think. In fact, even the notion of rank is not defined in ways that you would think. So, for tensors, you can have a explicit rank 3 tensor, which itself, so it's not a rank 2 object. It cannot be written perfectly as the sum of two rank 1 tensors. And yet, for any epsilon, there's an epsilon approximation that's rank 2. So even though it's rank 3, it's arbitrarily well approximated by rank 2 objects. That's really bad, right? Because that does not happen for matrices. If I take a matrix, there's one and only one best rank k approximation. In fact, if you take a matrix, then its best rank k and its best rank k plus 1 approximation are quite related. If you take its best rank k plus 1 approximation and ask for its best rank k, you get the same thing as if you went from the original matrix to begin with. That's not even close to true for tensors. They can share no factors in common. That's bad. Let me tell you what's even worse.
So the first one, what's different is that this is true for every rank?
There's a fixed, the second bullet point, or the third one.
What's confusing me is that for matrices, it is true that there are high rank matrices that are approximated by low rank.
Yes.
But
It's the quantifiers, right? There is one fixed rank 3 tensor, which is arbitrarily well approximated by rank 2 tensors. So even though it's not perfectly rank 3, for any epsilon, there is a rank 2 tensor that's epsilon close.
and that's not true for matrices?
No, not at all.
Determinant is positive then.
For example, the best rank k approximation comes from the truncated SVD. That tells you exactly how well you can approximate something for matrices. So it's because these things rely on arbitrarily large cancellations to get finer and finer approximations. All right, let me tell you one of the.
What do you mean by approximation?
All right, let me just do the example. Is there chalk here? Yep. Okay. So imagine I had a tensor which was the stack of these two matrices. This is not a rank 2 tensor. It takes a little bit of work to show that, but you can try it out and see that it doesn't work. Now the idea is that, this should be a 0 right here. So the idea is that what you can do instead, so this is your original tensor, what you can do is you can think about the tensor n, 1 over n, 1 over n, 1 over n squared, 1 over n, 1 over n squared, 1 over n squared, 1 over n cubed. This is a rank 1 tensor. And now if I subtract off this remaining n, then I get a rank 2 tensor. And yet how far I'm off is only dependent on this 1 over n squared type of thing. So I can make that arbitrarily small by creating larger and larger cancellations. So even though it's not perfectly rank 2, and you can prove that, for any epsilon, this one fixed tensor is epsilon close to being a rank 2 tensor. So this is, in tensor language, what this is called is that the rank is not the same as the border rank. The border rank is the notion of, its border rank would be 2 because it can be arbitrarily well approximated. For matrices, rank and border rank are the same. For tensors, that's not true, and that's a huge complication in computing the rank. Let me tell you another fact about it that's also equally damning. Let me do that. Okay, so in fact, I didn't even define rank for you properly because it depends on what field you're working over. So if you start with a tensor which only has real entries, then it turns out that there are tensors that have only real entries that have rank 3 when you require the factors and the factorization to only have real entries. But when you use complex numbers, they can have rank 2. So even if you started off with something with only reals, your best way of explaining it could be using complex numbers. That also does not happen for matrices. So I think I've basically made my point, but I think maybe the way to drive it home is that it's so bad that there's a very famous paper by Hiller and Lim that I think says it all in the title. Its title literally is "Most Tensor Problems Are NP-hard." So it's some laundry list of problems, and it's quite bad. But all this is meant to tell you is that the fact that there is actually an algorithm for doing something interesting with tensors is a bit of a miracle. And this algorithm has been rediscovered at least 4 times by my count. I'll tell you a little bit about why that is, because it's kind of an interesting story. But the idea is that under fairly tame conditions, this is the thing that I'm going to prove for you and then use. So these tame conditions are these underlying factors AI, BI, and CI. Well, imagine that the AIs are themselves linearly independent, the BIs are linearly independent, and the CIs have the property that no pair is a scalar multiple of each other. If you don't want that weak condition, you can just say AI, BI, and CI are all linearly independent. Then actually, the tensor that you get from it is unique in that any other tensor that has any other representation in terms of T as the sum of rank 1 tensors, which uses at most R factors, will actually use exactly R factors, and there's a way to pair up those factors to the true ones so that across it they're the same. So you get all of the factors right other than the trivial symmetries about permuting the rank 1 terms. So in fact, not only is it unique, but there's actually a simple algorithm to find it. And this was actually a little bit surprising because this was discovered in the psychometrics community who didn't have any language for talking about which of the theorems they were proving. All they cared about were uniqueness. Which of the theorems they were proving actually had algorithms to go along with it. So after this work, there were stronger uniqueness theorems that were proven, but were not algorithmic. And it's part of the reason that this thing got forgotten. It wasn't actually dominated by the later things because it actually did have an algorithm. So this has been rediscovered every decade since then. So I won't necessarily go into that, but it's kind of amusing. It's always fun when that happens. So I think the first time I wrote my lecture notes on this, I called it something else, and then I discovered it was discovered even a decade before I thought it was. So I called it the algorithm of Lurgans et al. But it was actually in a paper of Harshman and credited to some guy named Dr. Robert Generich, who I think is no longer in academia. So let me tell you this algorithm. So let me show you something you can actually do with tensors. So let's take our tensor T that has those conditions of Generich's algorithm. So all the AIs are linearly independent, BIs and CIs too. Let's pretend that's true. Now what we're going to do is we're going to take this tensor and we're going to hit it with a random vector x. So what do I mean by that is you take each of the slices through the tensor, and then x gives you a way to add up those matrices. So you use x as a way to collapse it down to a single matrix. So literally what you're doing is you're taking the ith slice through the tensor and adding it up by multiplying by xi and adding over I. And we do this for a randomly chosen x. Now the important thing is that tensors, everything works multilinearly. So if you want to understand what's happening, just think about what it does in the rank 1 case. If, for example, I took a rank 1 tensor, I guess the index I, it should have been k, but that's all right. So if I take a rank 1 tensor and I hit it with some vector x, then what I'm literally doing is I'm taking the inner product between c and x, and that'll be the scalar multiplier in front of a tensor b, right? And what that tells you is it tells you immediately what it does to a low-rank tensor. If you had that T was the sum of AI tensor BI tensor CI, then all you're doing is you're hitting the CIs with X, and that's giving you your new ways to scale and add up these fixed rank 1 matrices. Now, x is chosen uniformly at random from the sphere, and I'm going to use the following notation. So A is going to be the matrix whose columns are the AIs. B will be the matrix whose columns are the BIs. And this diagonal matrix will be a matrix whose entries are just the inner product of Ci and x. So what I'm getting literally when I compute x, when I hit the tensor T with x, is I get A times dx times B transpose. Now, if I do the same thing with hitting it with a random y, I get a different matrix, A times dy times B transpose, because now the entries in this diagonal are the inner product of the C sub i's and y. And now we're actually almost done, because the key idea is that given T, we have access to these two collapsed matrices. We choose x and y randomly. But now what happens if I take the first matrix that I got and multiply it by the inverse of the second one? I can write out explicitly what that is in terms of the factors that I don't have. And all that is it would be, the first matrix times the inverse of the second matrix. The B transpose and B transpose inverse cancel. And what I end up getting is I get A times dx times dy inverse times A inverse, which now looks awfully familiar because it's an eigendecomposition, right? And the claim is that if you choose x and y randomly, the entries in this inner diagonal dx dy inverse are almost surely going to be distinct. That means the eigendecomposition is unique and I can actually find this factorization. So now I'm basically done, because what would I do is I diagonalize a different matrix now. I just take the inverse of the first one times the second one. And that, what I'm going to get is I'm going to get B. I'm going to get the entries of B by that. The only remaining thing is how to actually pair up the A's and B's. And the point is that the eigenvalues of the first one are dx times dy inverse. The second one are dy inverse times dx. So they're actually reciprocals. That gives me a way to pair them up. And then I can actually solve a linear system to find the CIs. And you can prove that all of these steps are unique in that not only do I have a trajectory through the hidden factors that I don't know, but that's the only things that I could get as I do the steps of this algorithm. And you also don't need inverse. You should really be working with pseudo-inverse, but to keep things simple, I kept it this way. This is Generich's algorithm. This is how he proved uniqueness, was he actually gave an algorithm for finding the factors under pretty reasonable conditions from the tensor to begin with. And this is something that we could not do for matrices because it wasn't even well defined because of the rotation problem, right? So are there any questions about that? That's one of the main points I want to get across is Generich's algorithm. Yep.
Is there a deterministic algorithm?
I guess, yeah, that's a good question. I suspect not. And I suspect that would be difficult because you'd always be worried about, x could accidentally annihilate with some Ci, and then everything would go wrong. Like if its inner product was 0 with one of those, it would just be a missing factor that you would never get. So there would be basically no way to do that without completely redoing this algorithm.
So when you say that it's secure with high probability,
Okay, so what you would really need to do first of all, this statement is always working with the true values of the tensor. Now in reality, what you have is you have access to an approximation of the tensor, because a lot of times the tensor, as we'll see, comes from low order moments, your distribution. But what you'd really have to do is you'd have to do a stability analysis of this. And actually the stability analysis is a huge pain. Because the point is that you would need things like, first of all, if the CIs are not only not scalar multiples of each other, if they're somewhat noticeably different, then that'll tell you how anti-concentrated their entries are, and it'll tell you how distinct the entries of dx, dy inverse are. And then you have to do a stability analysis about a generalized eigendecomposition for it. So it's actually a huge pain, but there are references I can give you for this, and it was not in the original work. But it can be done, so I'll leave it at that. All right, so now actually let me tell you some more of the applications. We've actually already seen an application, which was factor analysis, that you really can find the factors if they are underneath a low-ranked tensor instead of a matrix. I can tell you a myriad of other applications. Let me tell you what are some of my favorites. So one of the first works in theory that actually used tensor decompositions for solving an inference problem was doing something for phylogenetic reconstruction. It's a little bit of a detour, but it's a kind of fun detour, and that's why I chose it. So we're not going to see the tensors for a few more slides, but let me tell you about this problem. So it's a very natural problem. Biologists love trying to find what's called the tree of life. So you take all the species that currently exist on Earth. These are called extant species. And what you want to do is you want to stitch them together based on how they evolved from each other. And you think about these breakpoints in evolution as themselves being the extinct species, which gave rise to some of the species that we see now. So, what is actually the underlying tree that describes which pairs of species are closest to each other? Now, the usual assumption in some of these models, which is a big assumption, is that they start off with the problem being, a large part of the problem being solved for them, is that they assume that among all of these extant species, that you've somehow found a way to align their sequences of DNA. And if you can do that, you can think about each of the indices into that alignment as themselves being described by a beautiful stochastic model on a tree. So this is a big approximation, but this is actually still close to the state of the art of what we can do theoretically. And the idea is that if you had these aligned sequences, you think about a single sample from this model as describing a single A, C, T, or G for each of the extant species. And what you have is you have some underlying distribution on the root. Which of the 4 states it's in. So I'll use sigma to denote the alphabet symbol. It could be things like ACTG, or it could be amino acids and proteins. But what you do is that's the seed of your stochastic model. And then along each one of these transitions, each one of these branches, you have a transition matrix that describes, conditioned on what the parent is, what the probability is for which of the different symbols comes out at the end of the day. So these are the underlying properties that determine the stochastic model. And you're assuming you get many samples from the stochastic model. And so for each sample, we observe a configuration of these symbols along the leaves. That's really like an index into these multiply aligned sequences. You can also do something similar like hidden Markov models are a very special case of this, where you start off with some initial distribution on this hidden state for X, and then there are matrices that describe your observations, and there are matrices that describe how your state evolves stochastically as you go along from left to right, which I won't really get into. But the point is, the first question before you even get into tensor decompositions is imagine you are given samples from this phylogenetic model. You could ask, can I even reconstruct the topology of the tree to begin with? So usually what one assumes is that these transition matrices are full rank. And then it turns out that there's this beautiful paper in evolutionary biology, mathematical evolutionary biology, of Steele, who showed that just based on the probabilities you can observe, the pairwise probabilities over pairs of extant states, that actually allows you to define a really bizarre function, which turns out to be a metric on the tree. It's not at all obvious. It's not even obvious it's non-negative. But this allows you to actually estimate the distance between different leaf nodes, and I won't get into that. But the basic idea then is what are called quartet tests. So if you think about Steele's metric as assigning lengths to the different edges, which themselves you're allowed to query the distance between 2 different extant leaves, because that function is something you can compute from your data, then what you're really trying to do is imagine you have 4 different leaves. Well, there are many different topologies of what their interconnection could be. You could think about A and D as merging before you get to B and C. The point is that just based on making pairwise distance tests, you can actually distinguish which of those cases you're in. So for example, in this case on the left, the sum of the distances from A and D to B and C is less than what it is in the other case, and that allows you to do tie breaking between it from polynomially many samples. But the upshot of it is that you can use these types of Steele metrics to actually find the underlying topology. And then there's a beautiful, this is one of the first places where Generich's algorithm is rediscovered. Sometimes it's called Chang's lemma. And what Cheng did was he showed that, that you could then use tensor decompositions to not only find the topology, but also to find the actual transition matrices along the edges. So the crux of it is the following idea. So imagine someone handed us the topology of the phylogenetic tree, because you can get these things from like Steele's distance metrics. Well, the idea is that now what you can do is you can think about rooting the tree arbitrarily. Imagine you root it instead at z, which is something that you're allowed to do in these settings, in these stochastic models. You could instead think about 3 different transition matrices, one that goes from z to b, one that goes from z to c, and one that multiplies all the transition matrices along the path and goes from z to a. And what you're really getting out is you're getting out a star graph where there's one node in the middle, and then you have these 3 leaf nodes on the outside that you get to observe. And the idea, and this is the take-home point, is where do tensor decompositions actually show up in this, is that they show up because when you look at the distribution over triples on those leaves that you really can observe, it's a low-ranked tensor. Why? Because conditioned on z, the leaves are conditionally independent. So if, for example, I want to know the probability that I observe some, the distribution on what I see at leaf A, at leaf B, and leaf C, then all it is the sum over this hidden state of what z is assigned to. That's the first thing multiplying it, times the product of their conditional probabilities, because they're conditionally independent. And what that literally means is that one of these guys right here is really the column of this transition matrix. Because that transition matrix tells us if z is sigma, what is the probability distribution over b. So what this means is that literally, what you're really getting, I guess let me actually go a little further. So what you're actually literally getting is when you get access to that thing, you're getting a low-ranked tensor that looks like this. It's some scalar multiple, which is the probability z is assigned sigma, times the outer product of some vectors that are themselves the columns of the transition matrix. And what that allows you to do is, this is some beautiful work of Mossel and Rock. They showed how you can then just apply tensor decompositions, do the stability analysis to actually provably recover the underlying transition matrices. And it turns out, I won't get into this, but this full rank assumption in Generich really is necessary. So one of the take-homes that I want to get, and I'll maybe take a slight pause right now, is when can you actually apply tensor decompositions? So here's one setting, is what we were able to do is we took a phylogenetic tree, and we're able to look at it and figure out 3 conditionally independent random variables. That's the mechanism by which we got a low-ranked tensor out of it. So in fact, that is what paves the way for all of the applications in inference and learning, is you want to take some stochastic model and get 3 conditionally independent random variables. How we did it for trees was we just rerouted and looked at the paths to get to 3 different leaves. But there are actually tons of applications now, so I'll tell you one more briefly. One is called topic models. So here, for example, you can think about, if you had some large collection of documents, like the collection of New York Times articles, then one of the popular ways to think about how this collection is generated is you think about the fact that many articles share similar topics. Some are about sports, some are about, Anoop's favorite team, the New England Patriots. And that's a longer story. And, but essentially what you assume is you assume in these topic models that there's some collection of topics which themselves are described as distributions on words. And so then the way that you actually generate a document now is your stochastic model, how you would actually construct an article, is that you choose one of the random topics according to some probability. That's the one and only one topic that your article is about. And then each of the words in your article is actually sampled from the corresponding column of this topic matrix. So you're generating the random words associated with that topic. Now, the idea is that these documents are somewhat short, so they're only L words long. So you can think about this pictorially as you have this topic matrix, which is word by topic, and each of its columns sum to 1. So each of its columns is a topic, which is a distribution on words. And then what happens is that the columns of W then represent each document, what its mixture is over different topics, or which of the different topics it is. So when I sample from my model, for example, the first document could be about only the first topic. And then multiplying A times W, I'd get a column in M, which is itself a distribution. And I could do that for all the other documents, but the point is that what I actually observe is a random sample from that. So the issue is that if you were actually given this really sparse, noisy term by document matrix, how could you go the other direction and actually find the topics that were used to generate the collection? So the idea behind all of this is that, so I'll tell you about, very briefly about a work of Anand Kumar et al., which actually shows how to give algorithms for learning the parameters of a topic model. And the idea really is, if we want to use tensor decompositions again, where can we find 3 conditionally independent random variables so that we find a low-rank structure underneath this model? So the idea behind it is that if you take a document, a random document from your collection, and you look at the distribution over its first, second, and third words, those are themselves conditionally independent random variables, because they're conditionally independent given what the topic of the document is. So that's actually literally how we can apply things to the pure document model, is that if we take a huge collection of documents and we look at the resulting distribution over the triple of what their first 3 words are, then literally what it will be is the probability that this hidden topic that describes the document is topic J times the outer product of AJ times AJ times AJ, which are just the conditionally independent draws from the topic matrix. So this is again a low-rank tensor that literally you can just apply Generich's algorithm. You just assume your model, you take enough samples to be able to approximate what this tensor is, and then you can find the tensor decomposition, which provably finds you the underlying columns of the topic matrix. So there's by now, I think, a few dozen papers that apply tensor decompositions to all sorts of problems. They also do it for things like community detection. But the main takeaway that I want you to get out of this really is the fact that tensor decompositions are very formulaic in how you use them. All you're doing is you're taking whatever stochastic model you care about and asking how can you actually manufacture 3 conditionally independent random variables. That's exactly the pattern that we used for doing something like phylogenetic reconstruction, was that our 3 conditionally independent variables came from triples of leaves. Now in the case of topic models, all we do is we look at something like the triples of the first 3 words in a document. That gives us 3 conditionally independent random variables that literally has a low-rank tensor structure underneath it. All right, actually, I guess I finished a little bit early, so I should take some questions and things. But really, to summarize what I hope you got out of this was more of a broad overview of tensor decompositions. Is the main point is that actually there are things that you can do with tensors that you can't do with matrices. The biggest issue is this rotation problem. Underneath it is the fact that a lot of times the way you apply matrix decompositions or factor analysis, you take some data matrix and you assume it's low rank, or you try and find a low rank approximation to it. But that has the issue that you can't tell the difference between different rotations of low rank decompositions. That means given a low rank matrix, you can't find the factors that generated it uniquely. But that problem completely goes away from tensors because low rank tensors are so much more rigid. Instead of being a single low rank matrix, they're collections of interrelated low rank matrices. That allows you to actually find the factors that were used to generate the low-rank tensor. Not only is it unique, but you actually have algorithms like Generich's algorithm, which is what I described, that give you algorithms for finding the factors. And that once you have Generich's algorithm as just a method to go from a low-rank tensor to the factors that defined it, you can then apply it in many different settings in learning, because the question really is, where in your problem are you going to find a low-rank tensor? So in a lot of those cases, it's just a matter of being clever about what statistics you can measure about your distribution that themselves look like a low-rank tensor, and it's really where are you going to find 3 conditionally independent random variables. So that's the mechanism by which you can apply tensor decompositions to these problems. Let me also mention, I think, what one of my favorite open questions is here, is, I gave you Generich's algorithm, really simple thing. And what it needed as an assumption, it needed that the AIs and BIs are linearly independent. So when you think about how large the rank of the tensor can be, if it's an n by n tensor, the largest rank that you could ever tolerate is rank n. Because beyond that, the a sub i's are certainly not linearly independent. So one of my favorite questions is that the reason Generich's algorithm was forgotten was because there are uniqueness theorems that work well beyond n. So there are things that work for 3/2 times n. There are even things that work for polynomial factors larger. So they work for n to the 3/2. And a very basic question is, we have an algorithm now for finding the decomposition under reasonable conditions of a rank up to n tensor, if it's n by n by n. Show me an algorithm that works for 1.1 times n in sub-exponential time. So that I actually don't know, because everything really does assume that these factors are linearly independent. I actually go back and forth on whether I think such a thing exists, but I would love to see it. So I'll leave that as my tantalizing open question. Someone solve it, that would be great. But that's it. So any questions you guys have? Yes. So what's true is that if you take a random tensor, not low rank, you just populate its entries randomly, then it's known that its rank almost surely will be omega of n squared. Now, in fact, within the algebraic geometry community, they care about what's the constant in front of that. But there are many more, not only NP hardness, issues, obstacles to computing the rank of tensors, things like that. But there are also some more serious, let's say circuit lower bounds obstacles, in that, a famous result of Raz shows that even though, a random tensor will have rank omega n squared, almost surely, if you had any explicit tensor whose rank was, n to the 1 plus epsilon, then you would actually get the first superlinear circuit lower bounds.
Wow. Okay.
So there's the issue that actually, even though we know tons of these things, everything is larger than rank n, and we even know uniqueness theorems that apply to those types of objects, that they're unique well beyond just rank n, that actually finding algorithms for finding the decomposition sometimes seems to go hand in hand with conditions that you'd have to fool in order to construct an explicit large rank tensor. So that's kind of an elephant in the room that makes things potentially tricky.
Do we even know explicit 1 plus epsilon times n rank?
Yes, so we know some constants in front.
Okay.
So that's why I think, for example, this is a somewhat attackable question, is that it's not in the realm of showing an n to the 1 plus epsilon, but I think all you can hope is actually improving potentially the constant or lower order terms. So there's actually a uniqueness theorem beyond Generich's. It's called Kruskal's uniqueness theorem that works up to 3/2 times n. But the catch is that, if you think about Generich's algorithm, if I gave you the factors, figuring out whether those factors meet his condition is a computationally easy problem. You give me the factors and I can compute whether the AIs are linearly independent, I can compute whether the BIs are linearly independent, and whether the CIs are not scalar multiples of each other. Kruskal's uniqueness theorem that works beyond it, it's actually NP hard to check his condition. So that's actually one issue, is that doesn't directly mean there's not an algorithm for doing it, but it's certainly another elephant in the room with going beyond n. In fact, I can ask even an even more embarrassing question. Give me an algorithm that works with r is n plus log star n. I know something that works with r is n plus any constant, but I don't know anything that works for any additive superconstant for it in polytime.
There are probably other I have a bunch of other questions, but if anyone else wants to. Well, so here you talked about third order tensors, this algorithm, fourth order, fifth
Yeah,
order?
okay. So that's a longer discussion. Let me tell you the short version of it. So there's actually a beautiful algorithm that, okay, so first of all, for a fifth order tensor, there's something trivial that you can do, which is that let's say you had a tensor, which, to keep my notation simple, I'm just going to use the same letter, each time. So let's say it was a fifth order tensor that you had access to. So one thing that you can do is you can actually flatten the tensor to make it be a third order thing. Because what you can do is you can pair up these two factors and squash them. So what you're doing is this original fifth order tensor is indexed by 5 tuples of numbers, but you're going to pair up the first 2 indices in that tuple and treat it like a single index. That isn't n, but now n squared. And this guy would be paired up so that it's a single index of n squared. And now what you have is you have a tensor, which is a third order thing. In fact, let me call it even sixth, right, to keep things simple, but the point is the same. And now I can take a sixth order tensor and create a much bigger third order tensor. So what I can do is I can trivially apply Generich to this and get an algorithm that works up to n squared for its rank, right? In fact, you can even ignore this last thing and still get it to work up to n squared because the conditions on CI were weaker. Now, there actually is a very interesting algorithm due to de Lothauer and some other people, which works for fourth order tensors. It works up to n squared. So that's genuinely different than this, and it's a really beautiful, complex algorithm. But that's one reason why some people are optimistic that, for fourth order tensors, you can work down to n squared rank. Maybe there's a hope that, for third order tensors, you can do something n to the 3 halves. But the issue is that whatever your algorithm is, should probably not give you a set of conditions for your uniqueness theorem that allows you to construct explicit third order tensors of large rank unless you want to prove new circuit lower bounds. So there is kind of an elephant. I mean, it's a longer discussion there, but I can tell you more offline too.
If you return to the original, so what are after 100 years, what could you say to Spearman? So
well, I would tell him I don't believe this. Yeah.
Or she should make another experiment to get another.
That's a good question.
Yeah.
Spearman's hypothesis was terrible, though. Oh, as in how could you get? Yeah, so that would be, so you could ask instead from the lens of tensor decompositions, you could ask him how can you find 3 conditionally independent random variables? So, if he believes that they're these adductive and reproductive things, intelligence, then, he believes that if you choose a, random student from your population and a random test from your population, that those give you 2 conditionally independent random variables. But I think the operative question is where would you get a third conditionally independent random variable? But that's a good one. I actually don't have a good answer for that.
So it doesn't say that he was. So first of all, does he have the rotation problem, or just the matrix was ranked more than 2?
So it was somewhat well approximated by rank 2, but the things he got were so noisy that you can't say anything about them anyways. But it's kind of shocking how, personally I think Spearman's hypothesis was incredibly naive, but it's actually had a big influence on modern psychology a little bit too much. And it also gets misinterpreted as Spearman's hypothesis is there are only 2 types of intelligence, mathematical and verbal, and then I'm even more against it. Because, the factors he found were orthogonal to each other. So they're very dense things, and yeah.
Other questions? I actually have a question. So it seems like, oh, sorry.
Oh, yeah.
No, so then, no. So common is better than organized closed.
Apparently, Goldman has a theory that there are 7.5. The number of intelligence is 7.5.
Where do you get a half?
The half is because the taste and the smell use a smaller part of the brain, and that sort of accounts for like a half of intelligence. 7.5 is a good guess.
I see. I don't know how to find the best rank 7.5 approximation to a matrix, but I'm sure tensor decompositions are better for it than matrix decompositions are.
Other questions? Just really fast. So I think the philosophy here is that you use the rigidness of the tensor plus the fact that you get nice algorithms for
Yeah,
rank 2
exactly.
tensors, matrices. So, okay, going to higher order tensors, are there any problems in the tensor world that are easy? So you could start at some higher, yet higher order tensor and then come down to a lower but not 2 order tensor. That's not really...
Are you asking if there are computational problems
Right.
which are easier for, let's say, order 6 tensors than for order 3?
Yes, exactly.
The only thing I know is this, is
Okay.
that you can work with a larger number of factors. But I think that's an interesting question, is if there is anything else beyond that.
Okay, cool.
Like finding the best rank K approximation or something, maybe it becomes easier for even higher order tensors than for lower order ones, because you can always find lower order ones from just flattening in the right ways. But I don't know anything that actually fits into it. So Generich's algorithm is kind of an island in a sea of other complexity issues. There are other ways to define rank. So for example, you mentioned there are other ways. But those are somehow less conducive to uniqueness theorems because they really are what you would get if you took the tensor and treated it as a matrix and applied all of the matrix toolkit.
In the example you've written on the board, it looks like n is not a constant. So you have a different tensor each time. Okay.
Yeah, so I think this should do it.
Right.
But that's a good question.
Okay.
Under this definition of rank of a tensor, is there a notion of eigenvalues or eigenvectors? Are there natural directions for the tensor?
So certainly there's no notion of an eigen decomposition because, for example, something that I think is still open is if you take a symmetric tensor, is its rank is the best the best decomposition of it? Can you assume without loss generality that it's symmetric? So that I think is actually still open. So I think there's very little hope to get a notion of eigen decomposition. You could also ask, can you even compute like the top eigenvector in the sense that can you find a cubic form on it that maximizes it? That's a spectacularly hard question. And in fact, I'll probably talk a little bit about that next time. So that's not even just NP hard, but it's hard in an average case sense for really basic things. And it's hard to even get within a polynomial factor of the right answer.